Hey guys, welcome back. Let's do a little bit of audio programming today, a little bit of signal processing. So this is Timbre. I've shown you this before. It's my audio engine and editor, and I'm developing it specifically to implement the audio for a game I'm working on. And in this game there will be lots of vehicles driving around, and a big part of the narrative is people using the radio to communicate with each other as they are driving around in vehicles. And so I basically need a way to add an effect on top of a clip of speech that will allow me to make it sound like they are using radios, walkie-talkies, military radios, police radios, whatever you want. You're probably familiar with the kind of sound I'm talking about. And so we'll implement a few filters today, or at least one. Let's start with one and see how far we can actually get in one video. So I've shown you Timbre before, how it works, and basically you put together these node graphs of nodes that do certain things, and then you can preview the thing here in the editor. So here we have a clip of music, for example, and we can play it. I've actually reworked quite a lot of the internals of Timbre lately, and one of the things I wanted to improve on was the support for filters. So we have this new section here in the wave asset node, for example. That's one of the new things. You can see that we can plug in filters, 4 of them specifically. That's sort of a hard limit for now, and I'll show you why in a bit. But basically we can do this. I only have one filter for now. That's the pitch shift filter. Used to be built into this node previously, but now you can just plug it in here. And we can set the pitch to something like 5, something ridiculous, and then you can see or rather hear the pitch changing. Perhaps even more interestingly, we can actually hook it up to a parameter. Let's call that pitch. Minimum something like -10, and the max something like +10. And then we can drive it. So we have a few parameters here. We have wet. This is basically how much of the filter that is active. Set to 1, so it's sort of fully active right now. We wrote 5 here. I think it's by default set to 0. So you can just set it in the node directly, but you can also drive it with something else. So now the value disappears because it's driven by this input pin here, and that is the float parameter, which we can control from up here. So if we start the sound and then we start to mess around with this. This is not specifically new, but the way we actually drive this is a little new when it comes to basses, because you can have 4 of these filters now applied. And why is it 4? Well, I've spoken about SoLoud previously. SoLoud is the audio library, which I definitely recommend you have a look at if you're interested in doing something like this yourself. This is a C++ library that is actually playing the audio put out by Timbre. And so SoLoud comes with a few different filters, which we can see here. Not this one actually. The pitch shift filter I've actually written myself based on some other tutorials, and you can definitely create your own SoLoud filters. There's like a whole API for that, but it comes with a few. And SoLoud by default supports up to 4 filters per audio source. That's why I have it set to 4 here. We can increase it, bump it up to more if we need to. but by default it's 4. That's why we have these 4 pins here. And right, so we probably need, we don't need a pitch shift filter for the radio effect, but we will probably need a couple of these that we have here. We need basically a high pass filter, and we need a distortion filter. And then on top of those, we can actually add some more effects on top of the sound. But we will need those definitely. And we can actually do that with some of these filters, even though you can't really find high pass or distortion filter here. The biquad resonant filter is actually a filter that can be used to implement all kinds of different effects. So low and high pass filters, as well as some kind of band, I think it's supposed to say pass filter here. So pretty interesting stuff. I've actually tried this just by hard coding it into the code, and it seems to work. So this is something that we would want to actually expose to Timbre. And when I say expose to Timbre, basically what I mean is that we'll create a node that you can just drag into the graph from here. If we filter this by the word filter, pun not intended, we can see that we only have one currently, and it is the pitch shift filter. So for this biquad resonant filter to be able to be used from Timbre, we'll have to actually implement it. And it has a few parameters that we need to set up, things like that. Then we have the other one, the distortion, and that can be done with the wave shaper filter. So it's mostly meant as a voice distortion filter. It only has actually one parameter to adjust the severity of the effect. So I think I'm gonna start with these two. We can, of course, if these aren't really up to the task, we can later on just implement our own. But they seem to actually produce quite nice results, and they're already actually part of the code base, since they are part of SoLoud. So let's start with the wave shaper, because this is the simpler one. So how do we do this? Let's shut Timbre down. We don't need to save that, no. That's fine. So the way we implement these nodes here, we need to actually create a couple of different classes, but we can pretty much just copy paste the previous one. We go to audio, so nodes, audio, and we have the pitch shift filter node here. As you can see, has some input pins, some output pins, some conversion code, convert to Sprinter. So Sprinter is the runtime component that actually executes these node graphs. And this is obviously C#, because the Timbre editor is written in C#, and also the Timbre library, which we are currently in here, which is sort of like the low-level library on top of which the Timbre editor is built. So we need two classes. We need one here in the Timbre library. This handles things like converting to the runtime format. We also need a graphical one. So we need another node here in the Timbre editor project. And here we have the pitch shift filter node, which handles the visual side of things. So you can see here that it has some like input boxes and things like this. And they basically need to have the same pins, called options here on the UI side, because we're using the ST node editor library, and an ST node editor calls these options. I typically call them pins, but the idea is the same. So we wanted the wave shaper filter. So let's start with just adding a new class here. And we can call this wave shaper filter node, like so. We'll drag it off to the right side, and I'm going to take the pitch shifter filter node here on the left. we can pretty much just copy paste this whole class. I think the wave shaper filter node would actually be even simpler than the pitch shifter filter node. And yeah, we'll probably need some of those as well. Whoop, I'm making a mess. Like so. And it derives from Sprinter data node base, which is a very simple class. It just actually contains a comment currently, and it derives from node. And this is my own node graph library. So there's a data side and a visual side, and the data side is essentially all my own code. The visual side is based on ST node editor, which can be a bit confusing, but that is how it works. Okay, so if we go back to the editor, actually. Oh yeah, it complains that we have actually multiple of these conversion nodes now for the same node type. Even though it's not really used, we can't have that. That's not cool. So in Timbre, if you drag a filter node here to the node graph, we have this output node here, which is currently actually unlabeled, but this is the filter instance that it outputs. Like I said, we have the wet parameter, which is something that all so loud filters have. It just basically means how much is this, how active is this filter. It goes from 0 to 1. And then we have a couple of other parameters here. With the wave shaper filter, we will actually only have one. We will have like the amount of whatever it was called. I think it's called amount. But we can see how that works. But basically, we will have the wet, which is like the overall strength of the filter, and then the amount, how much it will actually distort the effect. And so we will have two input pins, wet and amount, and one output pin, which is again the filter, just like with the pitch shifter one. So we can leave wet there, and it can be there as well. The other one we will want to have is amount. I'm just going to call it amount. I don't know how scientific that is, but that's fine. Input satisfied basically means that you can have custom logic here to determine if the inputs for this particular node is satisfied. They will essentially always be satisfied for this particular node, because you can always just write the wet and amount values directly into the node. You don't need to actually connect any input pins. And that's fine. And then we can already here, we can do the export part. This will be pretty easy. You might be wondering here, why is this in parentheses? Well, that's just because if you put the name in parentheses, it won't show up in the editor. I tend to keep, if it is very obvious what the output of a node is, in this case a filter, then I just prefer to like not show it there. But it's still actually called filter in parentheses. That's the output node. We have it here as well. And this is called amount. And so basically what this does is when we convert the data from C# classes essentially into something that the runtime can use, we need to package it together, and we have this thing called Sprinter, which then basically runs the node graph, but also allows us to package it in a format that it can do it. So we create a new Sprinter node. We get the nodes out of this, and we add the pins. We get the wet pin. We get the that's still called pitch pin. Let's call it amount pin, like so. And the conversion context. This is part of Sprinter. This again part of the system that converts between editor and runtime data. It has a function called add pin with float in place data. That's kind of a mouthful, but you can add pins. In this case, we have pins, but we might also have in place data. And that is when you actually have the data right there as part of the node itself, and you can edit it directly in the node without having to connect the input pin. So add pin with float in place data just means that it's basically just a convenience function that checks, is this pin connected to something? Then we get the data from that. If it's not, then we use the in place data, which is directly part of the node. The output pin obviously doesn't have any in place data. It will always return the audio filter, and we have the type here. This audio filter is really just an empty class. Might contain something someday here on the editor side, but basically just a way to limit what you can connect. You can connect an audio filter output pin to an input pin of the same type. These guys are just float, that's fine. Okay, so wet is 1 by default, amount is 0. Yeah, I think we can keep it at 0. We should definitely not make it 1, because distortion at 1 just tends to like blow out your speakers and ears and make everyone miserable. Let's start at 0. So it's 0 by default, and you have to bump it up yourself. Okay, so that's wave shaper filter on the timbre side. Now we need to implement it on the editor side. So technically, now that we have it on the timbre side, we can already we've had like a command line tool or something that generated these timbre node graphs. It could already export the data. It works quite fine. But if we want to actually edit this in a visual way, we need to add the node which handles that. So we go here. We had a bunch of usings there as well. Not sure we will need all of them. We might actually do that. And so I'll just rename all of these things like so. And this is the wave shaper filter. Yeah, so this attribute here actually just puts it in the node palette. So you can see here we can provide like a path where it is supposed to show up in the tree of nodes and with what name. Then need to give the name again. This is the name that shows up in the actual node. That's a little silly, perhaps. Could maybe have it so that it doesn't need to get it twice, but that's how it is currently. It derives from UI node base, which this is like a complete mess of a class, almost 500 lines, and it derives from st node, which is also a pretty huge class. This is part of the st node library. So this is in some ways much more complicated than the data one. But yes, so wave shaper filter like so. We will have a wet option. We call these options here because that is again what the st node library calls them. We will have the amount option. And we will call it amount as well. Right. Then we have the output, which is again called filter, and is again of type filter. And here's a little bit of unclear magic going on. We need to basically. I happen to know that like since we took away one of the pins, basically the delay. Now only have 2 input pins. Each pin typically occupies 20 pixels vertically, so I just lower that to 85. There's an auto size functionality, but it's not the best. so I typically don't use it. And here we want to call this amount. And we can take that away. Oh, amount. All right. There's a little bit of copying around of things here. So, what does all of this mean? Well, editor node data. First of all, if we go back to the data side, this is the thing that we just created. You can see that this also has editor node data attributes here. The editor node data basically just means that it matches something on the UI side, like a public float property called amount with this attribute. It matches it to this public float amount attribute on the data side. Because you'll be actually poking at this and moving this around, and when you set things, you execute commands in the editor, it will actually go in and then and copy the data over here to the data side. That's how you can get like undo working and everything. So that's what this attribute is. On the data side, you also have a serialized node data attribute. That just means that it serializes and deserializes it to and from the disk when you actually save this thing. And also when you load the Timbre project back up, this is the thing that will actually get read from the disk, and then it sort of creates one of these guys out of it to show it to you on the screen, and then it goes the other way around, like copies the amount from here and sets it here. This set field function is something that actually is used only by the editor. You can see here that it like runs commands to set node properties, things like this. Has to do with undo and redo. Stuff like that. Okay. So I think this is pretty much it. I think we have pretty much the C# code for this thing now written. The only thing we need to do now still is actually link these two guys together, and we do that with the node mappings class. So this just has a list of mappings here. You have basically the editor types here on the left, and then the data types on the right. And so we have wave shaper filter node, and we have wave shaper filter node. There we go. And now if we run this, you should be able to take these new things and put them in the node graph. So here we go. We have a pitch shifter, but we also have a wave shaper. Pretty cool. And we can, of course, connect these to this guy, like so. And we can create a new parameter here called distortion, something like that, right? And maybe we'll create the pitch one as well, for good measure. I think that was from -10 to tab. Unfortunately, doesn't work in that. I should probably implement that as well. Let's move those off to the side. Yeah, so you just hook these up, and you set that to pitch, and you set that to distortion, and there we go. Now we can save this, and it will work. It will. Now if we there's this test and or demonstration. Now if we load this back up, we have the things here, and they're connected, and everything is good. Now if we try to actually run this, bad things will happen. Sprinter node type Timbre nodes audio wave shape filter node not registered. Right. So now we're in C++. When you preview something here, it actually does like a mini export, the same as it does when you export it to the game. And what happened now is that it creates an instance of this event in the C++ code, feeds it to SoLoud, and when it encounters this new node, this wave shape filter node here, it doesn't know what to do. So we can ignore it, but that will probably crash the editor. So we'll just exit it. So now we need to actually go and do the same thing on the C++ side. So we have the... Actually, let me just quickly check, because I can't remember, because it's been so long. So the path that we actually need, I'm going to copy that. And so Timbre nodes audio, right? So that is this. It's this one here. Timbre nodes audio wave shape filter node. It encountered essentially the data for one of these guys. Again, this is just the visual side. This is the actual thing that matters. And the registration name here is, this is the actual thing. Timbre nodes audio wave shaper filter node. So we can basically just copy that path here and move it off to the side. Okay. Now then, what we can do is we can go to we can go to bases, and we can go to Timbre, and we can go to Timbre again, and nodes, and we can just copy paste this same pitch shift filter node on the C++ side as well. We call this wave shaper filter node, right? And then we go to, so that was the include. Then we have the source side. And so we have Timbre, nodes, pitch shift filter. We do the same thing here. Wave shaper filter node. Okay. Now we need to go to the actual C++ solution. We have Timbre here, C make lists. And we add it here as well. So, oh, did we actually... Nodes. Right, it's actually not there. It's just here. Yeah, I was thinking because like the core, yeah, this is the core library headers. They all start with Timbre. The nodes typically don't. The nodes I typically use the same name as in C#. Right, so we have the core headers, then we have the node headers, and we have the core sources and the node sources, and we'll add it here as well. Like so. And then we can just configure and generate, and it will reload it for us. Timbre is kind of nice to work with on C++ side because it's small enough to not be slow to work with, essentially. Right, so here we have the register, and we want to call it wave shaper filter node, and this is now the registration name. We need to make sure that we match the thing that is in the data. And this was the exact text that it was like, what is this? I don't understand. We can go to the CPP side, and we'll just call this wave shaper filter node here as well. Oh, we need to include the correct CPP file. Right, now we could actually build this, and it would build. And one more thing that we need to do is node registration. We need to actually include this thing here. Nodes and wave shaper filter node. Wave shaper filter node, like so. Right, so now we could actually run this probably. We would get some strange pitch shifting going on because obviously we copy pasted the node, so it still does the same as the pitch shifter node. But This is the way that we actually hook these things into the runtime side. You have a bunch of nodes that are part of Sprinter itself. Things like bool node, branch node, repeat, delay, random branch, remap float, integer compare, blah blah blah. But then we have a bunch of Timbre specific. These are typically related to audio, but not always. We have curve nodes, for example. I guess this could technically be in Sprinter, but it's here. Right. So, what do we need to do then? Well, we don't have pitch and delay anymore, right? We only have amount, and that would be one. So, whoa, misclicking here. Pitch shift filter. We can get rid of actually that. Yeah, actually we need to implement the pitch shift filter. That's true. Yeah, this node is actually going to be somewhat simple. Anyway, let's go through what we have. So pins here are implemented with just an enum. Typically I have like input pins, and then I have a space, and then I have the output pins. This is going to be a stateful node, just like the pitch shifter node. Some of these nodes are not stateful, like if you have an integer compare node or whatever, it doesn't need any state. It just does some calculation and then return the thing. But in this case, we will actually have state, and the state will typically just create a state. The state could, in this case, just be this pitch shifter filter itself, but I typically wrap it in a state here, because you never know if you actually want to have something else here. But of course, the way this pitch shifter filter works here is that it creates some state, just basically initializes the filter, and we need to create one of these wave shaper filters to actually put here instead of this pitch shifter filter. Get pin value is essentially what happens when something wants data from this node. Just like in the pitch shifter filter node, we can basically assert that the pin ID is the filter pin, right? It's the only output pin that we have, so it can't be anything else. And if it is something else, then that's not good. And the logic here will be essentially the same as in the pitch shifter filter, except we won't have pitch and delay, we will have amount. And what happens here is that like so, and we can do something like that probably. Yeah, what happens here is that when something wants to know what kind of filter this is, it gets its state. It then checks its parameters. So this is the part in the node graph where this node actually reads input from its own input nodes. So we should always have. I just wrote like a comment here that I assert that this boolean is always true, because we should always get something. Either it is connected to something else, so we have like another node driving this wet or amount value, or if not, then we get it from the in-place data. And then we set it on the filter. It complains here that too few arguments, but yeah, we'll get back to doing the filter. After that, we'll get the filter itself. Actually, we get a base class pointer, so Timbre filter. This filter guy is actually a Timbre pitch shift filter. We get a base class pointer. We reinterpret cast it into a uint pointer t, 64-bit pointer as a number essentially. And that's what we write to the output as the output value of this pin. So whenever you encounter a pin with the type of Timbre or type audio filter like this, this is what you're going to get. You're going to get a pointer essentially to a Timbre filter. Okay, so we can do the same thing here, amount, and we can get rid of the delay. And what this register shape wave shaper filter node function does is it basically just hooks up these well, first of all, it registers the input and output pins here on the C++ side. We haven't done that yet. And this is where the enum up here comes into play. So let's the system know here. Hey, what are we calling this? I mean, we could call this like hula baloo or whatever. Wouldn't matter. We're only using this inside of this one file, but we call it wet because that is what it's called. And we have to register these in like the same order as they are. Let's see, C# side. And we have to tell it the type so that it knows to allocate the correct size buffers, blah, blah, blah. Then we set up some function pointers. So yes, this is a stateful node. So create state. It will create a state. It will run this basically for us when one of these nodes is encountered. And it will call destroy state and then pin value. If you have execution pins, things get a bit more complicated, but we don't have any execution pins here, so this is enough. In the most simplest terms, a node can be essentially just one function, get pin value, and then we register the node. So that after all of this, we have the thing working. Right, so now we can't actually build this. If we try to build this, it will complain that it doesn't take 2 arguments. Of course, the bigger problem here is that we're still using a pitch shift filter. If we go and have a look what this looks like, it's not terribly complex actually. It holds a delay pitch shift filter, and it sets some things here. Basically, just forwards the values to the actual filter object. So we need to create one of these wave shaper filters in Timbre. So we'll go back to here, and we go back to here. Timbre delay pitch shift. It's not actually that. It is that guy. I'm gonna copy paste that. So wave shaper filter. Same thing here. Wave shaper filter, like so. And we need to add it here as well. So we added it to the nodes. This is not a node anymore. This is like a class. In theory, you could add a wave shaper filter to an audio source from code if you wanted to, and that could work, and that is perhaps something that we'll want to do at some point. But for now, we'll use the nodes. So then we need a node in between the filter object and the node graph. We need a node to actually hold that filter object. Okay, so we should have the new class here, and we'll just call it wave shaper filter. Wave shaper filter. This include is not what we actually want. Let's get back to that in a second. I'm going to move the CPP side here to this right side. I don't know what is left and right anymore. And that should be Timbre wave shaper filter, and now it should be better. Right. So here we will want to include so loud wave shaper filter. And instead of a delay pitch shift filter, we will want to have a so loud wave shaper filter. You can see that there's a wave shaper filter and a wave shaper filter instance. So loud internally creates instances of this filter as sounds are being played through the audio source. That is basically how it works. In here we want the wave shaper filter. Mount is supposed to be there, and also here. Amount. Right. So wet is set to 1, that's fine. And amount is supposed to be 0. I mean, these don't really matter because they will be updated anyway, but we can use the same values that we used on the C# side. That probably makes sense. Okay. What does this actually look like? Set params. Right, so this is just amount, like so. And here we have, whoa, not that. I want to copy just that thing. Wet. What doesn't it have wet? It should have wet. Or do we need to? We probably need to do so loud. Wet, yeah, that's better. And it should have an amount as well. Amount, and that should be amount. Like so. Okay, so this update for voice thing, this is something that gets called whenever Timbre has a voice handle, so basically a sound that is playing. And it knows that, hey, this filter is being used now to drive this sound. So then this is called automatically because it is basically it's in part here of the base class. All the filters in Timbre have this update for voice, and we just go through the main so loud object and then set the filter parameters. So this is to be able to adjust these parameters on the fly and actually have already playing sounds be adjusted. We need to have this sort of unified interface here. Update for voice, which always takes a voice handle and filter ID. So this is like 0, 1, 2, 3. We have 4 filters currently. And this is the way you actually update these parameters on the so loud side in real time. And get SLF just means so loud filter, and it returns the base class for that filter, right? Cool, so not very complicated at all, actually. This should be everything we need. And now we just go into our node right here. And we do timbre wave shaper filter. And we add, we change that to a wave shaper filter. And we don't even have an error there anymore. Okay, that might be it for this one filter. That might be it. I'm a little scared now, but let's try it out. So let's make sure our Timbre bridge is up to date, and it is. So Timbre bridge is the library that sort of bridges the C++ and C# side of things. Right. So now if we play this, we should hear something, and we do. So let's try the pitch first of all. That works. Let's reset that, and then let's try some distortion then. Hey, cool. Yeah, the thing with distortion is that it typically it increases the volume as well as the actual distortion. That's typically the case regardless of what kind of distortion you're using. Distortion filters typically increase the volume as well. So you need to be a little careful with this. That's cool. What if we add, I'm going to just call it param1. I'm not going to keep this I'm gonna keep this guy, call it param1, and we'll hook that into the wet. And it is set to 0 currently, so now we should be able to just up the distortion to, well, pretty high, and then fade it in like this, and it works as well. In this particular case, I think the wet and amount are kind of like superfluous, but there might be some subtle differences there in how it's actually handled, so probably a good idea to have both of them. Okay, cool. So that's one of the filters. That's one of the filters. I think I will do the other one offline. It's basically the same thing. So what I will do is I'll take the biquad resonant filter. This has a few more parameters, and in particular it has like let's actually go have a look at this real quick. What do we call it? So loud. Oh no, that's a wrong solution. So here, so loud biquadrant resonant filter. Right. So this has a few filter types. There's a low pass, high pass, and band pass modes that it can operate in, and so I'll probably have to have like a drop down in the node to allow me to actually select like something like this, like a float function. I can drag it onto nothing. You can have these kinds of drop downs here to like choose what mode to operate this node in. So probably something like that, and then based on that we will initialize the filter and then do the exact same thing. So that's pretty cool. When I have that, we could try to just dedicate one whole video to actually making a very cool sounding and completely real-time and dynamic radio effect. So that's something to look forward to. As a last thing today, maybe we can just quickly look at something like the wave shaper filter, right? What does this actually do? So we have a wave shaper filter in Timbre, which owns a wave shaper filter in So Loud. And if we have a look at what this actually does, then I'm going to go to CPP side. This is essentially the whole, well, not the whole, but the core, the heart of this filter. So you get a buffer in, and you're supposed to actually modify this buffer. Then you get some information about like how many samples, the time, the channel out of how many channels. This doesn't seem to actually use any of these things. And yeah, this is the distortion or wave shaping, but it's basically distortion. So you simply read from the buffer, you do something with it, depending on the filter, of course, and then you write it back out. And that's basically how the pitch shifting works as well. So I based this actually on a tutorial for Unreal for meta sounds. I don't obviously use Unreal or meta sounds, so I couldn't really use that code, but the math is basically the same. And yeah, here we have the delay pitch shift filter instance. Again, it has a buffer, and it modifies said buffer in some way. Oh, and I don't actually have the wet parameter apparently hooked up to anything, so I need to fix that at some point. But yes, that is that. Cool. A little bit of DSP today. So I'm gonna implement the other filter, and I hope to be back relatively soon with the next video in which we will design a cool radio effect, which we can then ideally apply to any speech. And it should sound fun. So, that's all I have for you today. If you have any questions or comments or suggestions, leave them below. And I hope to see you in the next one. Bye.